Hello everyone, welcome to lecture on microprocessor systems and interfacing. My name is Dr. Velayat Khan. I am an assistant professor at Comsats University, Islamabad WA campus. The slides used in this lecture have been edited from different sources, mainly including the two sources on the slide. The topics that are included in discussion during this lecture are software and hardware interrupts, mainly software interrupts. Interrupts are used in the modern microprocessors to increase the performance or efficiency of the microprocessors. Intel processors include two hardware fins, INTR and NMI. INTR is an interrupt request fin through which hardware components can send interrupt requests to microprocessor. And there is an NMI pin through which microprocessor receives hardware interrupts, but these two interrupt pins are slightly different. Interrupt request fin can be disabled or enabled, while NMI, which is non-maskable interrupt, cannot be disabled. Similarly, in the microprocessor, there is one hardware pin called interrupt acknowledgement, INTA, that stands for interrupt acknowledgement. That acknowledges the interrupt request through interrupt request pin. So whenever the microprocessor receives an interrupt through the interrupt request pin, that interrupt is acknowledged through this interrupt A pin, which is an output pin. Similarly, the microprocessor has also software interrupts instructions, INT, which stands for interrupt. This is an unconditional interrupt instruction. There is a conditional interrupt instruction, INTO, that means interrupt if overflow. So if the overflow flag is 1, then this interrupt will happen. And then there is a special interrupt called INT3. And then there is a bound interrupt. This is also a conditional interrupt. Apart from software and hardware interrupt pins, there is a flag bit called interrupt flag. This interrupt flag, and then there is a trap flag. These two flag bits are part of the flags register, or E flags register in the later more modern microprocessors. So these two flag registers are also used with interrupt structure, and then there is a special return instruction called IRET, slightly different than RET. So it's that's why I is used with this return instruction. So it's an interrupt return that transfers the control from interrupt service routine or interrupt handler or interrupt procedure. And in the later microprocessor 80386, 80486 and Pentium, then there is an interrupt return double interrupt instructions that returns from the procedure, but it's a double version of the INT interrupt return instruction. Interrupts are controlled or managed through interrupt vector table and interrupt vectors. So interrupt vector is basically a data structure that describes or provides the addresses, the offset and segment addresses of the interrupt service routine or interrupt service procedure. Interrupt vectors and vector table are crucial to understanding of hardware and software interrupts. The interrupt vector table is located in the first 1 kilobytes or 1024 bytes of memory. It addresses starting from the first 20-bit address till 003FFH. So this makes 1024 total bytes of memory. So the interrupt vector table is defined in this first 1 kilobytes of memory. This 1 kilobytes of memory defined in the starting addresses of the memory contains 256 different 4-byte interrupt vector. So each interrupt vector is a 4-byte data structure, and there are 256 different vectors. So 256 multiplied by 4 becomes 1024 bytes. So total space is 1024 bytes, and there are 256 total interrupts in this table, and each interrupt has 4 bytes. An interrupt vector contains the address, the segment and offset address of the interrupt service procedure. So interrupt service procedure is a small procedure or part of the program that performs a special task, and that task is in response to an interrupt, whether it is hardware interrupt or whether it is a software interrupt. But whenever an interrupt occurs, microprocessor transfer control to an interrupt service procedure, which consists of a number of assembly language instructions to address that interrupt, to answer, to respond to that interrupt, or to whatever the desired response should be that is defined in the interrupt service procedure. Here we have an incomplete interrupt vector table. This interrupt vector table as we earlier saw is defined on the initial address starting from 000H, and 10 is missing in all these addresses. Okay, and 2 zeros are in fact missing. And then going upward from this initial address, each interrupt vector is 4 bytes. So the first address from the 000 till 0003H, this divide error interrupt is defined. And then from 004 till 007, the single step interrupt is defined. And similarly, with a 4-byte interval, there is an interrupt defined. Because the size of each interrupt vector is 4 bytes, so these addresses are shown after 4-byte interval. And each interrupt is assigned a number. So this is interrupt 0 or interrupt vector 0, and this is interrupt vector 1, interrupt vector 2, and so on and so forth. So starting from divide error or the first interrupt 0 till there are 31 in total 32 interrupt vectors defined for the system processes. And then after that, these interrupt vectors are reserved for these operations, for these purposes. And then after the first 32 interrupt vectors, where the first interrupt is at 0 and then the last interrupt is at interrupt 31. But after these 32 reserved interrupts, there are user-defined interrupts as well, starting from interrupt vector 32 to the final interrupt vector, which is 255. So interrupt vector is located in the first 1024 bytes of memory. It addresses 000H through 03FFH, and there are 256 4-byte increase, segment, and offset in real mode. Okay, so here is the structure of the contents of an interrupt vector. An interrupt vector is a 4-byte data, and in these 4 bytes, byte 0, byte 1 has the 2 bytes, which are the new content of the instruction pointer or the offset of the interrupt service procedure. And the next 2 bytes, byte 2, byte 3, provides the 2 bytes or the new content of the segment where the interrupt procedure is defined. So just like the for jump, where the last 4 bytes were there to define the offset address to provide the new content of the instruction and the new content of the code segment. Just like that, here we have 4 bytes of data. So this 4-byte value has 2 bytes of the offset address, which is the new content of the instruction pointer, and 2 bytes of this vector represent the address or the starting address of the code segment. So basically, these 2 values, the offset address and the segment address, are loaded into the instruction pointer and the code segment register, and then the physical or memory address, the physical address or the memory address, is then calculated as with other addressing modes, left shifting the segment number by 1 hexadecimal digit and then adding the offset address. So the first 5 interrupt vectors are identical in all Intel processors. So here we have the first Intel divide error, single step in MI, 1 byte breakpoint, which is interrupt 3, and overflow, interrupt O, bound, and the rest of interrupts may change in different members of the family. Intel reserves the first 32 interrupt vectors. So starting from interrupt vector 0 till interrupt 31, these interrupt vectors are reserved. The last 24 vectors are user available. These interrupt vectors starting from vector 32 till 255. These interrupt vectors are available for users. Each interrupt vector is 4 bytes long in real mode and contains the starting address of the interrupt service procedure. So the starting address is actually provided in the form of the first 2 bytes contain the offset address, which is the content of instruction pointer, and the last 2 bytes of the interrupt vector contain the segment address. So an interrupt vector completely describes where the interrupt service procedure or the interrupt service routine or interrupt handler is defined. The instruction pointer and the code segment together would provide the physical address or the memory address of the interrupt service procedure. In the Intel, the first 5 interrupt vectors or interrupt types are common in most of the microprocessors family, most of the Intel microprocessors. The first vector, which is type 0 or vector 0, is the divide error interrupt, and this interrupt happens whenever the result from a division overflows or an attempt is made to divide by 0. So whenever a division is computed and a value is divided by 0, or whenever the division overflows, for example, the result of division is stored somewhere in a small variable or memory, then this would give a divide error. In most of the cases, this error is given when some value is divided by 0. So if you try to divide a value by 0, this interrupt would be enabled, this interrupt would be executed. So this is a divide error interrupt. The vector number 1, starting from location 004 till 007, is the vector type or interrupt type 1. This type is single step or trap interrupt that occurs after execution of each instruction. Whenever an instruction is executed at the end of execution of that instruction, this single step or trap interrupt occurs. But this occurs only if the trap flag is set. if the tray flag is set, then this interrupt would occur, and if the tray flag is not set, then this interrupt would not occur. So the tray flag is used in the flags register to enable or disable the debugging feature. So this interrupt is related to the debugging feature of the microprocessor. So when this interrupt is accepted, tray flag is cleared or tray is disabled, so that interrupt service procedure executes at full speed. So normally when an interrupt service procedure is being executed, it is better to disable the interrupt flag and the tray flag so that other interrupts are not accepted and the interrupt service procedure is executed in full speed. Similarly, type 2 interrupt, which is the vector 2, is related to the non-maskable interrupt. So it's related to NMI or non-maskable interrupt. This NMI or non-maskable interrupt occurs when a logic 1 is placed on the NMI input pin to the microprocessor. So whenever a hardware wants to interrupt the microprocessor through a non-maskable interrupt, this interrupt happens when this cannot be disabled, so that's why it's called non-maskable interrupt. While the other interrupt, which comes through interrupt request fin, that interrupt can be disabled by disabling or clearing the interrupt flag. But this interrupt NMI cannot be disabled, so it's non-maskable. It cannot be disabled. For example, power failure. Whenever power fails, this interrupt is sent through NMI. NMI or interrupt request. These are the two interrupt fins in the microprocessor. Interrupt vector 3 or type 3 is a special 1-byte instruction written as int space 3. So this is a variation of interrupt instruction. So this is 1-byte instruction, while other interrupt instructions are 2 bytes represented with int followed by a number, that is a vector number. But this special instruction is 1-byte instruction, and this is used to access. This is normally used to store a breakpoint in a program for debugging. So this is a special variation of the software interrupt int. Similarly, interrupt 4 or type 4 is overflow interrupt. It's a special vector used with INTO instruction. So INTO is a conditional interrupt instruction, software interrupt. The INTO instruction interrupts the program if an overflow condition exists. So if overflow flag is 1, then this interrupt overflow interrupt can happen. But if the overflow flag is 0, this interrupt will not happen. Similarly, type 5, which is the final interrupt type common in all of the microprocessors, is the bound instruction. It compares a register with boundaries of values defined in the memory. If the contents of the register used with the bound instruction are greater than or equal to the first word in memory and less than or equal to the second word, no interrupt occurs, because the value stored in the registers is within the bounds or within the limits. If the contents of the register are out of bounds, a type 5 interrupt issues or comes. For example, bound AX comma data. So interrupt would happen if the value, the 16-bit value stored in the AX register, is less than the memory location data and the next location data plus 1. So AX is compared with the value, 16-bit value stored at data and data plus 1, and it is also compared with the 16-bit value at data plus 2 and data plus 3. So interrupt this interrupt checks if the value in the register is within the bound. If the contents of the register are out of bounds, then type 5 interrupt occurs. So if these conditions are satisfied, then no interrupt occurs. But if these conditions are not satisfied, then this would mean that the value in X register is out of bound. So if the value in X is less than the 16-bit value in the memory stored in these addresses, or if the value in X is greater than the 16-bit value stored in these two addresses, then the interrupt would not occur, or otherwise interrupt would occur. So okay, so more about the bound instruction. If the contents of the register are out of bounds, are out of type 5 interrupt issues. So it interrupts the bound AX data. It's a conditional interrupt. It would occur if this condition is satisfied or if this condition is satisfied. Okay, so software interrupt instructions, the same instructions but little more detail. So 5 software interrupt instructions are available to the microprocessor, and INT are very similar. It's a 2-byte instruction, and it's a special instance of this instruction, which is 1-byte instruction. Bound and INTU are conditional instruction. This checks for a value in the registers to be within the bounds, and this checks for the overflow flag. IRET is a special interrupt return instruction. So bound has 2 operands and compares the register with 2 words of memory data, as we saw an example of this on the previous slides. I interrupt O checks or tests the overflow flag. If the overflow flag is 1, that means overflow has occurred. So INTU calls the procedure whose address is stored in address and interrupt vector type 4, because in INTU is overflow interrupt, and it's a type 4 interrupt. So that's why whenever an overflow occurs, interrupt O would trigger the vector number 4, and the vector number 4 contains the offset and segment address of the interrupt procedure to respond to this interrupt. So if the overflow is 0, interrupt O performs no operation and the next sequential program instruction executes. And the interrupt N instruction, this INT means interrupt and N is a vector number. This interrupt instruction would call the interrupt service procedure at the address represented in vector number N. So this N is a vector number. So for example, interrupt 4 would access the interrupt vector number 4 from the interrupt vector table, and then that interrupt vector number 4 has 2 bytes of offset address, which would be loaded into the instruction pointer, and 2 bytes of the segment address, which would be loaded into the segment register and would provide the starting address of the segment where the interrupt procedure is defined, and the offset address would provide the address of the first instruction of the procedure. Interrupt 3 is, I just said, is often used as a breakpoint or interrupt because it is easy to insert a 1-byte instruction into a program. So breakpoints are often used for debugging software. The IRET, its interrupt return instruction, is a special return instruction used to return from both software and hardware interrupts. Whenever software and hardware interrupts are executed or happened, the interrupt service procedure is accessed, and at the end of that interrupt service procedure, to return from that procedure, IRET instruction is used. So much like a for return, it retrieves the return address from the stack. So whenever a software interrupt is executed, it pushes using push F instruction the flags onto the stack. So the status of the flag bits are pushed onto the stack so that it can be retrieved later on when IRET instruction is executed. It clears, microprocessor clears the T and I flag bits because the interrupt service procedure is being executed, or the control passes to that procedure. So it's better to disable the trap flag. It's better to disable the interrupt flag so that no more interrupts are received while this interrupt is being addressed or this interrupt is being handled. Similarly, it pushes code segment onto the stack because the new content from the interrupt vector would be loaded to the code segment register. So that's why the old content is pushed onto the stack so that IRET instruction would get it back so that the controller would return to the application or to the program or instruction where the control has left. Similarly, the microprocessor fetches the new value for code segment from the interrupt vector, as I said, and pushes the instruction pointer or extended instruction pointer onto the stack, so that the offset address of the current ongoing instruction or the instruction that would be executed next is stored onto the stack so that it can be retrieved later on. It fetches the new value for IP or EIP from the vector. Remember that in the interrupt vector, there are 4 bytes, so 2 bytes would cover the instruction pointer content and 2 bytes would cover the code segment content. And then it jumps to the new location addressed by the code segment and the instruction pointer loaded from the interrupt vector. Here are the fins used in the 8086 microprocessor, but these fins are available in the later microprocessors as well. So here in the 8086 microprocessor is given with 40 fins in dual inline packages form. In this package form, the microprocessor has 20 fins on one side and 20 fins on the other side of the microprocessor. So the hardware pin interrupt request is shown here. It's pin 18 on the left side, represented with INTR, and there is an incoming arrow that represents that this pin is an input pin. So interrupt INTR interrupt request. This is triggered input. This is sampled or during the last clock cycle of each instruction to check for if there is any interrupt request. If any interrupt request is pending, if a software or if a hardware interrupt has occurred, the processor enters the interrupt acknowledge cycle so that interrupt would be addressed or responded or handled. This signal is active high, so whenever a 1 is sent through this pin, the interrupt is triggered and internally synchronized with the clock, internal clock of the microprocessor. The next pin is pin number 17, which is NMI, and this is a bidirectional pin, non-maskable interrupt pin. Through this pin, non-maskable interrupt request can be sent whenever NMI input is activated. A type 2 interrupt occurs. So when a request through this pin arrives, microprocessor knows that interrupt type 2 would be accessed, so the interrupt vector 2 is accessed, and when interrupt vector 2 is accessed, the 2 bytes of the instruction pointer are updated, and the 2 bytes of the code segment are also updated, and the interrupt service procedure defined for the non-maskable interrupt is accessed and executed, and the microprocessor then respond accordingly. Similarly, there is an interrupt acknowledge pin represented with INTA. This is pin number 24. Interrupt acknowledgement is an output used in response to interrupt request input to apply a vector type number to the data bus connections D0 to D7. So whenever an interrupt request arrives, when that interrupt request is to be addressed or to be responded, this interrupt acknowledge pin, which is active low, sends an acknowledgement and a vector type number, which is an 8-bit vector type number. So because there are 256 interrupt vectors in the vector table, so 8-bit is sufficient to identify or to number each interrupt vector uniquely. So that 8-bit value is sent through the data bus connection D0 to D7, and this would identify the vector number to be executed, and that vector number would provide the interrupt service procedure, which includes some instructions to be executed to handle this interrupt. So microprocessor has 3 pins: interrupt request, NMI, and interrupt A, to access, to receive interrupt request, and to acknowledge interrupts. And similarly, there are 2 flags: interrupt flag and trap flag, to enable or disable flags and trap debugging a feature of the microprocessor. And there is interrupt return instruction as well, that would cause the control to return from the interrupt service procedure to the original instruction from where the when interrupt happened, when an instruction was being executed while an interrupt happened. So that is after the end of the execution of that instruction, interrupt is addressed, and the control has to come back to the same place where the control has left. So interrupts, there are interrupt instructions as well. In a program, execution of a program can be interrupted either through hardware interrupts, or the execution of a program can be interrupted either through the software interrupts. So software interrupts are from within the software. So an software instruction generates an interrupt, while hardware interrupts come from external devices and external components through the interrupt request pin or through the NMI pin. The difference between interrupt request pin and NMI is that interrupt request interrupts received through interrupt request can be disabled. When interrupt flag is set to 0, then interrupts are disabled. No interrupt can be received through the interrupt request pin, but NMI, non-maskable interrupt, cannot be disabled. So interrupts can still be received. And when interrupt are acknowledged, this is acknowledged through the interrupt acknowledge